Section 8.1 is on applications involving right triangles. I have a couple definitions up here that we've already seen this semester, but I just wanted to include them again to be thorough. So first thing here is we have a triangle in which one angle is 90 degrees is called a right triangle. We've been working with these all semester. The side opposite the right angle is of course called the hypotenuse, and then the other two sides are called the legs. So far what we've done in this class is we've been looking at angles in standard position on the XY axis, and we've been forming right triangles by dropping perpendiculars to the x-axis. Now what we're going to do is we're going to work with freestanding geometric objects. So here you see a few different right triangles. They're just floating around somewhere on my page, all willy-nilly. They're not on the XY axis. These are freestanding geometric objects. So we're kind of shifting our focus now to a different type of trigonometry. So the way that we label right triangle is always going to be the same. The angles inside the right triangle here, we're always going to label these capital A and capital B. And then the hypotenuse is always going to be, the right angle, which is opposite from the hypotenuse, right? The right angle is always going to be capital C. So the angles we label capital A, capital B, and the right angle is capital C. The sides, we label them with the same letter A, B, C as the side they're across from. So you can see in these pictures, here's angle A, across from that is side A. Here's angle B, across from that is side B. Here's angle C, across from that is side C. Angle A, side A, angle B, side B, angle C, side C. The angles are always given with capital letters and the sides are always given with lowercase letters. Okay, so now there's a couple things we've already seen in this class. We've seen the Pythagorean theorem. We know a squared plus b squared is equal to c squared. This is true for any right triangle. A and B have to be the legs and C has to be the hypotenuse. The other thing we know about a triangle is that all three angles always add up to 180 degrees. So if we have one right angle, that means that the other two angles have to always add up to 90. So angle A plus angle B always adds up to 90. Okay, so what we're going to do in section 8.1 is we're going to solve triangles. So when we're asked to solve a triangle, what we're going to do is find the missing lengths of sides and angles. Now your textbook and your homework will tell you how many decimal places to round to. Sides, typically they have you round to 2 decimal places, and angles, they typically have you round to 1 decimal place. Now, one benefit of this section that you guys will like is that when we're doing freestanding geometric objects like these triangles just floating in space, we always measure that in degrees. We usually only use radians when we're doing something circular or something that's oriented on that XY axis in standard position. Okay, so anytime we're doing a triangle, otherwise a freestanding geometric object, we're going to use degrees. So for this chapter, you will need a scientific calculator. You'll be allowed a scientific calculator on the next exam. So if you want to go ahead and pause this video and go find your calculator so you can follow along with me today, that would be great. Okay, so we'll just jump right into an example, and the good news is you guys already know how to do all of this trigonometry from the previous chapters, so it's really nothing new. It's just applying it to a different type of problem. So let's solve the triangle. And here we're given a picture of a triangle, and we have angle B is 41 degrees. Here's angle A, so that makes this side A. They tell us side A is 9, here's side B, and here's side C. Okay, so to solve the triangle means to find all the missing angles and the missing sides. So we need to find angle A, we need to find side B, and we need to find side C. So angle A is the easiest place to start, so let's find angle A. We know in a triangle, the 3 angles add up to 180, which means these 2 angles add up to 90. So that means that A is 90 minus 41, which is 49. Next up, we need to find one of the other sides. So let's find side B. Okay, so our process for using trigonometry to solve these triangles is step 1, we're going to choose an angle of reference. Now what I like to do is I like to circle my angle of reference so that it's very, very clear which one I'm using. So we can use either angle A or angle B. So here I'm picking angle B as my angle of reference. The next step is I want to label my sides opposite, adjacent, and hypotenuse based on that angle of reference. Okay, so based on where this angle is, the side across from it, that's opposite. The side next to it, that's adjacent. And then of course, across from the 90 is the hypotenuse. Now I would recommend that you actually label them opposite, adjacent, hypotenuse like this and not OAH. The reason why you don't want to use OA and H is because we have an A here and we have an A here. So if you have another one that's A, it can be really confusing as to what you're using. So if you get in the habit of just writing opposite, adjacent, hypotenuse, that makes it a little bit easier. Okay, next step is we're going to find a trig expression. That has what we're looking for. As the only unknown. And then step 4, we'll solve it. Okay, so I'm going to do the work right over here. So choose an angle of reference. We did that. We labeled our sides. Now we're going to find a trig expression that has what we're looking for as the only unknown. So we're working on finding side B. We know side A. So if we want B to be our only unknown, we have to use one unknown and one known. So we ask ourselves what trig expression relates opposite and adjacent, and that happens to be tangent. So tangent of 41 degrees is equal to opposite, which is B, over adjacent, which we know is 9. Next step, we multiply both sides by 9. We get B is equal to 9 times tangent of 41. Here, I'll show you the work here. Multiply by 9, multiply by 9. All right, notice how I've written this. The 9 is out in front of the tangent. It's not inside the tangent. It's not tangent of 41 times 9. Okay, so on your calculator, what you want to do is a couple things. First, we're entering this angle in degrees. So you want to make sure your calculator is in degrees. Calculators can switch between radians and degrees. They're all a little bit different. So if you can't figure out how to do it, Google, for example, how to switch between radians and degrees on a TI-30 or whatever you might have. Go ahead and type this in your calculator. You're going to want to hit 9 times tangent of 41 and then hit equals. You should get 7.82. If you're not getting the same answer as me, either you're still in radians or your calculator actually might require you to type this in backwards. So if you don't get this answer, the other thing you might try is hit 41 and then hit tangent and then hit times 9 and then hit your equal sign. If you need more help with your calculator, feel free to, of course, send me an email or stop by the Math Center or ask in recitation for some help. Okay, next up, we want to find side C. Of course, we know Pythagorean theorem, a squared plus b squared is equal to c squared, so we could use that. But since we're working with these right triangles in a different way now, let's go ahead and use trig. So let's find side C. So what we want to do is set up a trig expression that has C as our only unknown. So we look at C and then the given was A, so that's adjacent and hypotenuse. So I have cosine of 41 degrees is equal to adjacent, which is 9, over the hypotenuse, which is side C. Now here we have our unknown in the denominator. So the first thing I'm going to do is multiply both sides by C to get that out of the denominator. So then I have C times cosine of 41 is equal to 9. Next step, divide both sides by cosine of 41. You get C is equal to 9 divided by cosine of 41 degrees. All right, in your calculator, go ahead and type in 9 divided by cosine of 41 and hit equal. You should get 11.93. Again, if you're not getting the same answers as me, check that you're in degrees, and then also check the order in which you need to type these in. If your calculator requires you to type them in backwards, 41 and then cosine, you're gonna have to do it in a couple steps and write down the numbers. You are allowed a calculator for exam 3, so if you want to make sure you get a calculator now that you're comfortable using on the exam, you can get some practice with that. Once we have our answers, the good news is we know some things about triangles to check this. So I filled in all my answers up here. The first thing we should check is that our 3 angles add up to 180, and they do. The next thing we should check is that the scale of these sides makes sense. So how large or small they are, they should all be, for example, these are 7, 9, and 11. So they're all in the same scale. So what you want to be on the lookout for is if you have one that's like 7, 9, and 500. Those aren't on the same scale. In a triangle, it doesn't make sense for one side to be ridiculously larger than the other things. The other thing you want to check is that the smallest side is opposite the smallest angle. So our smallest angle is 41. That's opposite the 7. The next angle is the 49, that's opposite the 9, and then the largest angle is the 90, that's opposite the 11. So you should check smallest angle opposite smallest side, middle angle opposite middle side, largest angle opposite largest side. Of course, you can check Pythagorean theorem that a squared plus b squared is equal to c squared. Here, because we rounded on the sides, you might not get an exact same answer, but you're going to get something really close. Let's do another one. Okay, so let's solve this triangle. We have that side A is 4, side B is 3. We don't know what side C is, and we don't know what angle A, and we don't know what angle B is. So this one's a little bit different than the previous example, but our methods are going to be the same. So we want to start by finding angle A, finding angle B, and finding side C. Now this one we aren't given any angles at all. The last problem we were given one of the angles. So what we want to do is we can start by finding an angle or finding a side. It doesn't really matter. But here we can use the Pythagorean theorem to find the third side and get that quickly. We know that a squared plus b squared is equal to c squared. So we have 4 squared plus 3 squared is c squared. 4 squared is 16, 3 squared is 9, so 25 is c squared, which means c is 5. Now look, this is our good old 3, 4, 5 triangle that we've been working with quite often this semester. This is a really nice Pythagorean triple. So all semester we've been working with this 3, 4, 5 triangle, but we've never talked about what these angle measurements are. So now we're actually going to be able to find those. So let's start by finding one of our angles. So let's find angle A. So our steps are the same 4 steps from the previous problem. Step 1 is to choose an angle of reference. Since I'm finding angle A, I'm going to pick angle A as my angle of reference. The next step is to label the sides opposite, adjacent, and hypotenuse based on that angle. So cross is the opposite, next to is the adjacent, and then C is the hypotenuse. The next step is to form a trig expression with what you're looking for as the only unknown. So we want to use something with angle A, and then the sides that the problem originally gave us were the opposite and the adjacent. We also know that the hypotenuse is 5, so we could set up sine, cosine, or tangents. Here, because the problem gave us these 2 sides, I'm going to go ahead and use those. So I have that tangent of A is equal to the opposite, which we know is 4, over the adjacent, which we know is 3. Now we're working on solving for angle A, so we want to get rid of the tangent. So what we're going to do is take inverse tangent of both sides. Now remember, when we went over these cancellation properties, we had to ask ourselves if this number was inside the domain. And because we're working with a triangle, these 2 angles have to be less than 90. And our restriction for inverse tangent was negative pi over 2 to positive pi over 2. So these are less than 90, so that's definitely in our restriction. So here you never have to worry about that because we're working with these right triangles. These are always going to cancel for you in this section. And you get that A is equal to inverse tangent of 4/3. All right, on your calculator, you should have an inverse tangent button. It is most likely right above your tangent button. You might have to hit second or function to get up there. So go ahead and try inverse tangent of 4/3. You should get 53.1 degrees. Your calculator's in degrees, so the answer that you get is in degrees. These parentheses are important. You have parentheses buttons on your calculator, so you should hit inverse tangent parenthesis 4 divided by 3, close the parenthesis, and then make sure you hit equal. The last angle here is really easy. We want to find angle B. We know that A plus B is equal to 90 since this is a right triangle. So B is 90 minus angle A, which we just figured out was 53.1. So that makes angle B 36.9 degrees. I have 2 more examples for you, and these are the same types of problems, but they are given in word problem form. So they might look a little different right off the bat, but they're all just going to boil down to finding a triangle and then solving for the sides. So next one is we have a tower that is 57 feet tall, casts a shadow that is 82 feet long. We're asked to find the angle of elevation of the sun to the nearest degree. All right, the first thing we want to do is draw a picture. So here we have a tower, and that is 57 feet tall. It casts a shadow, so the shadow is of course on the ground. And the shadow is 82 feet long. Make that a little bit longer, try and get this to scale. All right, we are asked to find the angle of elevation of the sun to the nearest degree. Okay, so we have to use a little bit of common sense here. If the shadow is on this side of the tower, that means that the sun is up here somewhere. Now, what is this asking us to find? The angle of elevation of the sun. What this is asking is if you were standing on the ground right here and you looked up at the sun, what angle does the sun make from the ground here? So angle of elevation means how high up is the sun in the sky, okay? So we're looking for this angle X. Our process is the same as before. We circle our angle of reference because this is the angle we're looking for. We're going to use this as our angle of reference. I'm going to label my sides opposite, adjacent, and hypotenuse. And we want to find that angle. So in the next step here is we set up a trig expression that has what we're looking for as the only unknown. So what do we know? We know the opposite and adjacent, so that's going to be tangent of x is equal to the opposite, which is 57, over the adjacent, which is 82. Next step here, we want to solve for x, so I'm going to take inverse tangent of both sides. These are always going to cancel out in right triangles. You don't have to worry about that. So we get x is equal to inverse tangent of 57 over 82. So in your calculator, go ahead and type in inverse tangent of 57 over 82. You should get 34.804 degrees. This problem specifically asked us to round to the nearest degree. So to round to the nearest degree, we look at this 8, it's higher than 5, so we round up to 35 degrees. Now this is actually a pretty cool real world problem. If we know a height of a building or height of a tower or height of any object, we could actually, with a tape measure or some sort of tool, measure the length of the shadow at any point during the day. Then using this trigonometry, we can actually calculate the angle of elevation of the sun. Whereas if we tried to actually measure this, it would be really impossible without some very expensive equipment. So using trig though, we can figure out the exact angle that the sun is in the sky. So this one's kind of neat. We'll do one last one here. Last one, I have a trail with an inclination of 17 degrees, leads from a hotel at elevation 9,000 feet to a mountain lake at 11,200 feet. The question is, how long is the trail? So this is an interesting one. It might happen up in Tahoe somewhere. So what we have is we have a hotel. So let me draw my hotel. And the elevation of the hotel is 9,000 feet. And then we have a trail that has an inclination of 17 degrees. So what that means is, compared to a flat line, this trail is 17 degrees. It's inclined, it goes up 17 degrees. At the top of the trail, we have a mountain lake. And now maybe you're wondering why I'm not an art teacher instead of a math teacher. There's my lake. And we know the lake is at 11,200 feet. The question is, how long is the trail? So here's our trail. We go from the hotel up to the lake. Maybe we're a hiker and we want to know how long this trail is. All right, so we're going to circle our angle of reference. The process is the same. This is the only angle we care about here, so that's going to be my angle of reference. My sides are opposite, adjacent, and hypotenuse. What we need to know is we need to set up a trig expression that has x as the only unknown, so we need to know one more of these sides. So we look at this information and we know that we have started at 9,000 and gone up to 11,200. So if we've risen from 9,000 to 11,200, that means we've traveled up 2,200 feet. So the opposite is going to be 2,200. Okay, so the next step is we set up a trig expression that has these two. So we have opposite and hypotenuse, so that's sine. So sine of 17 degrees is equal to opposite over hypotenuse, which is x. We are solving for x, so our first step here is to get our variable out of the denominator, so we'll multiply both sides by x. I get x sine of 17 degrees is equal to 2,200. Next step, divide both sides by sine of 17 degrees. I get x is equal to 2,200 divided by sine of 17. All right, so in your calculator, go ahead and punch that in. We get 7,524.67 feet. And just pay attention on your homework. You'll be told how many digits to round to. So this one here, I rounded to 2 decimal places. We should ask ourselves, does this make sense? This side's 2,000, this side's 7,000. Sure, that makes sense. What we want to be on the lookout for is things that doesn't make sense. If this side is 2,000 and this side is like, say, 10, that doesn't make sense. Also, for triangles and geometric objects, we should never have a negative answer. So just some things you can check, like the real world, does your answer make sense? So the length of this trail is 7,524 feet. So it's at like 1.33 miles, something along that line. So yeah, that makes sense.